Alright. Hi students, welcome to experiment 6, Esterification. In your experiment to make an ester, we will be using an alcohol and a carboxylic acid. Now when you see this equation here, you see that this occurs in a reversible manner. You have a double arrow and the reaction is always incomplete. So the product here includes the water and the esters. You need to know what is the structure of the alcohol and esters you are using for your experiment. As mentioned earlier on, since this reaction is irreversible, we need to increase the yield of the product, which is our ester, towards the right side by shifting the equilibrium position to the right. So using Le Chatelet's principle, we can use excess of the reactants on the left, either the excess of the alcohol or the excess of the acid, or to remove water so that we can get more esters. In this reaction, you'll be using a lot of corrosive reagents such as concentrated sulfuric acid, also known as battery acid. The carboxylic acid that you are using in this experiment is also highly corrosive, so do take note, do not come into contact with them. Battery acid. So this concentrated sulfuric acid is highly corrosive. It can even burn a hole through your latex glove that you are wearing. It won't help. You get this burning sensation and your fingers will feel hot. Very dangerous indeed, so take care when you see that there's a drop of liquid on your fume hood and you suspect that it is not water or it may be some other chemicals. It could be sulfuric acid, so do not just take a piece of cloth and wipe it. Use a piece of tissue and see whether it corrodes, because it could very well be some concentrated acid. So the alcohol, the carboxylic acid, and the esters produced, they are all flammable, toxic, and irritant. Any fire nearby is a no-no. You could set the whole lab ablaze, and you're going to come back maybe half a year later to complete your experiment. And certainly no drinking of that alcohol. No drinking. No tasting of the esters, no matter how good it smells to you. And please refrain from rubbing your eyes, no matter how itchy it is. Use the eye wash at the basin if you need. And always transfer the chemicals inside the fume hood, because all of them have very strong smell. We can call it fragrance to some people, but not everyone will receive it as fragrance. So do be responsible and courteous. In this reaction setup, we have to use a dry 50 ml round bottom flask. Now the question you could ask yourself is, why must it be dry? As mentioned just now in the equation, using the Chatelet's principle, if it is wet, you have some water, it will shift the position of equilibrium towards the left hand side. That will reduce our yield of the ester. Additionally, your alcohol and the acid are anhydrous, so if you have some water inside the round bottom flask, you may hydrate them. You have some heat of dissolution. So you add inside a stir bar, the alcohol and the acid. It says 4 equivalents here. So how do you measure? Equivalence here means the molar ratio is 1:4. 4 times of the acid compared to the alcohol. And from mole concept, you can find out the mass of the acid. From the mass, look at the density, you find the volume, because I believe that all these acids that you're using are in liquid state at room temperature. And after adding the chemicals, always cap it, not with your fingers. So this is not good. Okay, I don't want to see a thumb. I don't want to see a thumb. This is not good. No using thumb. Using a stopper or the cap, because they are too fragrant to some of us. So while swirling and cooling the flask, very slowly and carefully add the concentrated sulfuric acid. That's 0.5 equivalents. Again, you measure by calculating the number of moles required, converting to the mass, and then after that calculating the volume needed. So you add the con sulfuric acid dropwise. Now what happens if you add it too quickly? Now think about when we dilute sulfuric acid. Should we add the acid to water or water to the acid? The answer is we add acid to water. The reason is because When we do a dilution of corn sulfuric acid, we'll use a beaker, okay, and here we put water. So this is H2O. Okay. Now this is not good enough. We have to put it in a ice bath. Why ice bath? Because the dissolution of sulfuric acid is a very exothermic process. So here we put ice water. Okay, and then slowly we will add corn sulfuric acid. Inside here, what must we have? We must have a stir bar that keep on spinning, because if not, you have a localized heating. So this sulfuric acid, right, will come down to this portion and dissociate to form your ions, and they get solvated, so releasing a lot of energy, a lot of heat, and then we have localized heating, and this heating over here could vaporize some of the water that you have inside upwards. Not good, because right, suppose you measure 100 ml of your water. Okay, you calculated the concentration required after dilution, so you need 100 ml of water, but then after adding some concentrated sulfuric acid, it gives you only 98 ml of water, because 2 ml has been vaporized but the heat evolved from the dissolution process. So it's very critical that you put this whole beaker in an ice bath with stirring and add the corn sulfuric acid dropwise. Okay? Now in another scenario, suppose we put it in an ice bath. Ice bath. This is my corn sulfuric acid that I need. We put water to it. What happened? The first drop of water goes in, solvate the corn sulfuric acid, and all the heat will vaporize all the water here. So you see steams, H2O, white fumes. Okay, this is certainly what you don't want. Alright. So after that, assemble the apparatus and reflux it for 1 hour. What does it mean by the word reflux? Reflux. Does it mean heating? No. Reflux means you have a reflux condenser here. Okay, you put a condenser that's made of glass linked to a round bottom flask. So stirring, inside you have the glass tubing inside. Cooling water goes round and round. Remember, water goes in from a bottom and comes out from the top. Okay? The top here can be open or sealed depending what is the condition of your experiment. So in some cases, when you do research next time, you need to be in the atmosphere. So you have to put a rubber atom connected to a balloon, okay, of nitrogen gas. But in this case, it is not necessary. You just got to leave it to the atmosphere. Now, reflux doesn't mean heating, because sometimes in your reaction mixture, the heat evolved could be enough to vaporize your solvent or the compound, and that's why we got to have a condenser above it to cool it down first before anything could vaporize up. Imagine your solvent is there to contain the reactants for them to interact, but being a volatile solvent, the heat evolved, vaporize everything out, so you have no solvent, and that will nullify the effect of the interaction. See this sign here? Very corrosive, so don't try anything funny. In the workup, you got to cool the reaction mixture to RTP. Okay, and you have to cool it slowly. Do not rush for time and put the whole reaction mixture into the ice bath, because the thermal gradient could be too large and your RBF may crack. If it cracks, all your compound leaks out and you got to restart the experiment, only if you have time. So after that, add 15 ml of DI water into a 100 ml separatory funnel. Slowly transfer the cool reaction mixture to it. So again, because you have excess acid use, it could be a bit corrosive and irritant. So be careful, wear glove all the time. Do not allow any contacts with your skin. Then you rinse the RBF with about 5 ml of DI water, okay, and add this to the separatory funnel. Now when I circle 5 ml here, does it mean that you have to measure using a measuring cylinder exactly 5.0 ml? No, this is what we call the workup, is to quench the reaction. It's a quencher, so even if you have 4.5 ml or 6-7 ml is okay. It is alright, because it's not really a reactant here. So next, carry out extraction and drain the aqueous layer. Do you still recall how to carry out extraction? As shown in the last video, I have provided you with a link so you can check it out on the YouTube. Okay, be confident. With more practice, you will do it fine. Okay, and drain out the aqueous layer. Now, which is the aqueous layer? You see a separatory funnel that's tapered at the end. Okay, you don't call this the tap, you call this a stop cock. Alright, here. So normally you see 2 layers. Now how do you know which layer is the one that you want? How do you know which one is the one that you want? So as a practice, if you are not sure, okay, we will keep both the top and the bottom layer in 2 separate conical flasks. Okay, so one layer drain out, the other came out, and then we can use some tests to ask ourselves whether it is the aqueous layer or the organic layer. Now the way you can tell is, right, the solvent that you use. If you're using CH2Cl2, which is very dense, it should be at the bottom compared to water. If you're using ether, which has a density lower than water, then it should be at the top. Ether, okay? So ether versus water. If it's methylene chloride against water, then water will be at the top. Clear? Okay. Alternatively, now you have these 2 layers, you can just drop carefully water dropwise, and you see if it flows down and sink through the top layer. If it does, that means water doesn't interact well with the top layer and it must go to the bulk solution that's aqueous to the bottom layer. But if you don't see this line of flow of this droplet, that means the top layer is aqueous. Additionally, you're going to transfer 10 ml of saturated sodium bicarbonate, or you can say sodium hydrogen carbonate, NaHCO3 solution into it. This is to neutralize the excess acid. Now gently swirl the uncapped funnel. Why must it be uncapped? Because you have carbonate or bicarbonate with acid that will give off CO2. So there's sudden expansion of the gas inside. Okay, if you seal it, what happens is it may explode. And there have been cases I've seen before students, they keep it on, they shake it so vigorously, they feel that it's bulging out, but yet they want to contain it, and after a while, their hands couldn't take it anymore. So the whole thing just flow out, and they got very low yield for the esters, and the whole fume hood smells so fragrant. They spent an hour to clean up the mess. Okay, so what you do is you add your bicarbonate inside the separating funnel. Okay, add inside, and then you see effervescence, okay, of gas coming out, okay, bubbles here. Wait until you see no bubbles evolving from the liquid before you carry out the extraction. Okay, we don't want explosion. No. So which layer has the chemicals that you want? The ester is what you want, right? Okay, which layer to keep? Like I mentioned before, you keep both layers, and then do you go and smell which layer has the ester? No, you got to use your chemistry knowledge to think. Esters has a higher solubility in the organic solvent, so it should be inside the organic phase. So you extract and check the pH of the aqueous solution. Why do you have to check the pH? Because if it's still acidic, you got to use more of the bicarbonate to neutralize it. Now, so you perform the final extraction of the organic layer with 10 ml of the brine. What's brine? Brine is saturated sodium chloride. And transfer the organic layer into a clean, dry 50 ml conical flask. Why must be dry? Again, because this is your organic layer. If it's wet, when you do a distillation, you have more than one solvent. You have your organic solvent and water has a pretty high boiling point. It will take a while for it to come off, and it will slow down your procedure. So collectively, how many extractions will you conduct? Do a count. It should be 3, minimum 3. In your future research, you may need to do maybe even 4 to 5 times, because if your yield of your compound is very low, or you get maybe 0.01 millimole of your compound, and suppose this is already 100% yield, you have to extract many times so that you can get more of your compounds that can be recovered. You don't want to lose any single bit out because it's so rare. After like a 20-step reaction, I want to savor and collect as much as we want, because maybe this took you 3 months to make. You get me? Okay, but in this experiment, 3 is good enough. Alright? Watch the video first and get yourself familiarized with it. Okay, pretty clear, go through in your mind what's going to happen before you embark on the experimental procedure. Next, dry the crude esters with anhydrous magnesium sulfate or sodium sulfate given by the lab. Both are hygroscopic and absorb all the water that's present, which is still remain in the organic phase, and let the solution stand for this amount of time. Filter the crude product into a clean and dry 25 ml RBF. Why this volume? Why not 50? Why not 10? It depends on the amount of esters you expect to get. So if you get about 10 to 15 ml of ester, the size of the RBF should be about 25. You see, it's about half or midway there. This is too small if you expect this much of esters to be evolved. Now for the purification, we're going to set up a simple distillation and collect the product in a pre-weighed glass vial. This could be a plastic vial, so do not be alarmed if you don't find it's glass, okay? It doesn't have the king kong sound. And then estimate the heating temperature based on the boiling point of the product. Different esters have different boiling points, so do not assume that they all boil at the similar temperature. It will not. And then label your glass vial and submit the products for grading. We will look at the appearance, the amount of products, and possibly the smell. So the setup display, this is how it looks like for the purification. Your round bottom flask is here, and the thermometer should be placed at the mouth of the T-shaped adapter, okay, slightly below the mouth. Of course, here you can measure the volume of your ester, or you can directly put your vial here. So you may have to wrap the T-shaped adapter with aluminum foil before heating, because you have to contain the heat, and you see there's some cooling part. This part is exposed to the air. If you do not wrap it with aluminum foil, there's a chance that the vapor of the esters may condense here and go down again. It will not exit to your vial. So the heating needs to be powerful. Should we use stir bar or boiling chip? It's written in your lab manual. Okay. And do not dry everything up. One way to increase the effectiveness of this distillation is to add dry sodium carbonate, dry as in solid, okay, or sodium bicarbonate, into the RBF so that any remnants of H plus can be neutralized and will not interfere with the distillation. So for the cleanup, as you know, our chemicals are very fragrant, very fragrant. So always put the stopper at the bottle at the round bottom flask before and after reaction when you move around the lab. Once you step outside the lab, right, once you move the chemicals outside the fume hood, always keep it on. For solid waste, filter paper, cotton wool that used to do a simple filtration, keep these in the common fume hood bin. Do not just dispose it at the bin next to your fume hood. Don't do that, the smell will permeate throughout the whole lab. This is not desirable. And wash the glasswares inside the common fume hood. The common fume hood is the one that's quite big, and you have some waste solvents here, chlorinated, non-chlorinated. Okay, wash it inside, don't wash it outside. Now for many organic experiments, we have to characterize our compound form. So if you have to do IR, you can do it on the same day or the following day, latest, okay, the day after your lab. But for NMR, if you have to do it, you have to complete the sample of the NMR on the same day. No deadline extension. Make sure you don't bring any impurities into the NMR preparation. So how do we prepare the NMR sample? So we are scanning the hydrogen proton NMR sample. Typically we will need about 20 to 30 milligrams of the sample dissolved in this much of an NMR solvent. Okay, CdCl3, we call it chloroform D, so CdCl3. Okay. Again, must be a dry test tube. If it's wet, you see a very strong signal for the presence of water, the hydrogen in water. So the mass of the sample can be weighed or estimated. How do you weigh it? So we use the dry NMR tube. Weigh it, copy it down in your lab manual, and add the sample. Weigh again. The difference in the mass will be the mass of your sample inside. And does the accurate mass matter here? Does it matter? You just need to add enough sample so that your NMR spectrum doesn't look too vague. That means, right, if it's too dilute, your signal will be masked by the noise. If it's too concentrated, it will take a very long time to resolve the signals also. So do it just nice. After the sample dissolves, transfer the solution in a clean and dry glass dropper, and then transfer it into the dry NMR tube carefully. So this NMR tube is quite expensive and it's very fragile, made of thin glass walls, so please don't use too much force, because you break it, you hurt yourself, you jeopardize the lives of your lab partners, the people around you, me, instructors, lab officers. Okay, be careful. Always stay safe. Safety comes first. Nothing trumps it. After you are done, cap the NMR tube and label the tube properly. Ensure that the height of the solution is about 4 to 6 cm in the NMR tube. If you need to add more solvent, top up, but top up with the right solvent, CdCl3, if that's the solvent used. So how do we label on the NMR tube? Tuesday group, TU, and then plus the fume hood number, Wednesday, WE, fume hood number, and so on and so forth. After that, you add on your matrix number at the back. So ensure that the height of the solution is about 4 to 6 cm in the NMR tube. Again, it's just an estimation, so please, if you really want to measure it, use a piece of ruler and you get 3.9 cm. Does it mean that you could add more solvent? It's fine. But if you get something like 2.5 to 3 cm, then you have to top up more solvent. But it should not exceed 6 cm because CdCl3 is very expensive. It's very hard to manufacture it since the abundance of deuterium on Earth is quite low. So do not waste a solvent, it's really costly. For your analysis and discussion, please answer the questions in your lab manual. So record all observations when this is observations. Any color change. So observations in science means any gas produced, color change, solid form, fumes, layers, etc. Okay, and then calculate the percentage yield of your purified compound. Emphasize in your lab report, we emphasize a lot what you write is clear and concise. For question 2, you have to interpret IR and NMR spectra if you have done it and evaluate the purity of your final compound. Okay, so you see whether the signals regards only your compound or there are other foreign signals that could be due to your reactant because your purification wasn't that good. So where do you interpret your spectra? Directly on it. So you don't have to use another piece of paper. Okay, no need. You just see this is a spectra. Suppose here it is TMS. Okay, at 0 ppm. ppm stands for parts per million in NMR, parts per million. TMS is tetramethyl-silane. That's used as a reference. It is used as a reference because it has very high stability, high thermostability. What else? It has only one proton environment, so it can be used as a standard, and compared to the proton attached to a carbon, all these are connected to, compared to the ordinary proton in an organic molecule, because it's Si, this is silicon, so these protons here are more shielded. So you have a chemical shift lower than what we want to inspect. So it can be used as a reference. Okay, tetramethylsilane, TMS, tetramethylsilane. So suppose this is a spectra. Okay, a triplet and a quartet. This represents a CH2CH3 group, triplet quartet. So you can tell me, okay, where is a triplet? Triplet belongs to this signal. So you can label, this is HA, okay? And if you think that this is the HB, they label HB here and HB. You have to also look at the integration, and this represents the amount of protons in that environment. So if this is HA, then you should see maybe 3.0, and let me change the color. And maybe this is 2.00. So the ratio is 2:3. It could also be 6:4, or any other numbers as long as when you do the ratio between these two peaks, you should get 3:2. I'm just saying as an example. Now furthermore, for the analysis and discussion, you have to use your own experimental results. Do not use your friend's one. It is all individual work. Use your own words. Be creative. Be original. Proper referencing. This has been taught to you. If not, look out for the guideline. And once again, concision and clarity. Your NMR spectrum will be available within a week. So you have to collect the spectrum from the lab, the synthesis lab. You can only collect your own spectrum. You can't help your friend. This is all individual. We will check the spectrum and see if it matches your metric number. So please don't try anything funny. Use your own spectrum. No matter how good or how pretty it is to you, okay, just submit it. It is experience to learn. So thank you. Have a nice day. See ya.